So here we are in Class 5, Introduction to FEA. We're going to use finite element analysis for deflection. So this is Chapter 19 of Shigley. We jumped ahead. And the big idea is we have a condition, a model we've made, and we're going to discretize that model using finite element analysis and be able to find the deflection there. The overall big idea, we make a model, we discretize it, we find the stiffness, or the computer finds the stiffness, we apply the loads, and from that, with the loads and boundary conditions, we find the deflection. From that, we can get the strain, and from the strain, we get the stress. That's our big idea in FEA. So the model is generally considered the geometry of the thing that we're looking at, and the loading conditions, which include the forces we place on there, but also the boundary conditions. And those two things can make a big part in the quality of our results. We discretize, which is often called to mesh the thing. We break it down into usable parts, these elements, and there's only so many of them, therefore they're finite. And these elements are joined by nodes at the joints of the elements. Internally, it finds what the stiffness is based on the geometry and the material properties, usually Young's modulus, and to a lesser extent, Poisson's ratio, to be able to find the stiffness. And we create this stiffness matrix called K. And it's a symmetric, in the simplest case, a 2x2 matrix. It could be larger 3x3 matrix or 1,000 by 1,000 matrix, but it's a big matrix, this K. And we apply these constraints, which would be loads and boundary conditions, and then solve for this equation, F is equal to K times U, where U is a displacement. One of the biggest computational tasks is to invert the matrix K in the F equals KU so that we can solve for U's. And then once the U's are found, we're able to use geometry to find strains. In the simplest case, that would be the strain is equal to the displacement divided by the initial position. And then we solve for stresses by way of using Hooke's law. This kind of big idea, this big idea, something to consider, that what we're really first looking at it's a displacement solving routine. And from displacements, we're able to come to a conclusion about the strains and thereby the stresses. Generally considering what we wanted, the overall idea is we converge. That's the big operative word. We converge to a solution by way of having enough elements and nodes so that we are sufficiently getting closer and closer to reality. Reality can be best measured by displacement because we can physically measure displacement, whereas we can't really physically measure stress. So generally speaking, in FEA, we can have convergence in displacement much quicker and accurately than we can for stresses. So there are a bunch of different codes. this is not an inclusive rendering. One of the big names is ANSYS. You can get a student version. It's like a 32,000 node limited version of the thing. You can get Abacus, which is also a big name, maybe a little bit lesser extent than ANSYS. And there's a student version that's limited to 1,000 nodes, which is not a whole lot. The biggest name historically was Nastran, and the NAS, as part of Nastran, is NASA. It was a code that was developed by the U.S. government for the going to the moon, famously, and because it was a code that was open source, it's also been adopted by other companies. So MSC, McNeil Schwendler Corporation, was what that used to be stand for. It was one of the pioneers. McNeil Schwendler being some of the people that helped to develop the NASA code for their finite element analysis. But there's others like NX that have so there's a Nastran NX, and there's other Nastrans, and you can find a student version edition for about 5,000 nodes. Also in the automotive industry, there's an FEA code named Altair. There's others, and it really depends on your industry. What's out there. So it's good to know a bunch of different FEA codes if that's what the field that you're going into. COMSOL is a big player for multiphysics. SolidWorks simulation is what I tend to use. Of course, Autodesk is big player too with they're the parent company for AutoCAD, and they have Fusion 360 has an FEA code. But there's also open source codes available out there. Good to know a lot of codes, but they all share a lot of the similarities. It's when you're learning to use any of these, there is a learning curve, and I think one of the shortest learning curves is with SolidWorks simulation, in my opinion. So here's a demonstration. I'm just using a door handle here to show some stress calculations. We're going to be using displacement specifically in this class, but the next step after that is often stress. So here is I picked a problem. I'm not sure it was a homework problem it was a homework problem that I've used before, where I just came up with some geometry, and you can see it has this bent looking door handle thing, where I've applied loads at the end of it right here in the X direction, Y direction, Z direction. And it's 24 inches in the dimension A, 16 in the dimension B, and 12 inches in the dimension C. So you get kind of an idea. And it's got a cross-sectional dimension of 2.5. I didn't think a lot about this before I put it together, just so you know. I mean, I didn't like think about like how much load I was applying onto the thing. So here's the geometry values as part of this. Here's the free body diagrams and the equivalent moments that get generated, and the stresses for a particular spot, right? So that's what I want to do here is look at a point. So this point B right here that we're looking at. Combining those together, where we have bending and axial combining for their normal stresses, and torsional shear, this is the 29.34, and the transverse shear. And there you go. There's the answer. So something that we haven't looked at yet in the course, this being class 5, is a very useful stress parameter that we call von Mises stress, where we take sort of the equivalent stress, and we also call this distortion energy theory, by the way, giving it away, in a way to find a single number that is comparable to the strength data that we get, which is from an axial pull test. So this is like, sometimes von Mises is also called equivalent stress. The equivalent stress is 72.14. So if we run through an FEA and we take a solid, here we have the SolidWorks model I've generated. Notably, I have made these little lines, split lines, so that I could find a precise location that matches with what the original problem is, which is at point B right here. Right, so I have cut this thing up with these split lines. I've also moved it away from the wall. You can see there's a fillet at the wall, but I have made it so that the geometry, so this exact point right there should match up with what the problem is. I want to make a apples to apples comparison. And so right here at that spot, this is a pretty rough mesh. I've meshed this thing up, and I put the boundary conditions, which is the constraint here at the wall. And I've also applied these loads right here. And then I solved, and I got 67.48. Now recall that here I got 72.14. That's a pretty good amount of a distance, but that's a crude stress. I could definitely improve this, perhaps. I'd say definitely. I don't know that for sure, but by making a finer mesh in the location where I care about the stress. I'd also point out that something that happened as I'm solving this is I get a warning that we have a large deformation. I had to use a different solver. So some of that 6.46% difference could be because of the mesh, but it also could be because the loading condition is so large that it's actually not a linear solver anymore. The hand calculations that we're using were based more of a linear approximation. But 6%, 6.5% in general, from my experience, is not a bad correlation. There are, but if it really matters, we need to investigate further and do some more FEA techniques. But this is just the beginning as a demonstration to show you the hand calculation versus the FEA results. And then displacement was also something that I could also measure as part of that. And I've put the undeformed shape kind of superimposed in there so you can kind of see a little bit of it. Notably, well, it actually doesn't say what the scale is. This says the scale is 1:1. No, it does say that what the scale is. Scale is 1:1. So that's a lot of displacement, a whole lot, 1.93 inches, compared to what you might expect in a most FEA. And once again, you got to remember what the original scale of the problem is, which is to say that it was 16 inches. So we have, coming back to here, like 2 inches in a 16 inch. That is a large deflection. Here's another example. I think I've used this in the previous problem where we had 3.77 millimeters in the y direction, excuse me. This is what you have. Also, like a 3% difference, 3.655 millimeters versus 3.77. So we're in the ballpark. Once again, this is proportionally correct. So you can kind of see how thin these the actual thing is as a 10 millimeter compared to the geometry. So this is how basically FEA works, right? With a lot of simplifying assumptions that we're going through here, where I've already mentioned F equals KU, right? Force is equal to stiffness times displacement, and we invert the K matrix to be able to get the displacements and solve for it. Then we use the what we find from the displacements and we're calling that matrix B here, this relationship, to find the strains. B is often called the strain displacement matrix. And then we're able to find stresses from strains, which is just Hooke's law. Typically, the assumptions that we make here, the material is isotropic, which means it has the same material properties in every direction. It's easier to think about materials that are not isotropic. Some of them would be like carbon fibers or fiberglass. They're not the same in each direction, right? So they're laminates. There's many other different types of materials that are not isotropic. We tend to say, well, okay, we're dealing with steel and aluminum, so they're isotropic materials. Material is linear. Well, we have to make sure we're staying within the range of where the material is linear. Notably, aluminum, which we use a lot, doesn't really have a linear range. If you look at the stress strain curve for aluminum, we make an assumption of linearity and all the time with respect to that, but it's not linear. Also, it's elastic. Okay, that's really related to the linear range. We haven't surpassed the yield strength, basically, is what we're saying there. Deflections are very small, so we've already seen with one of the analyses that I did with FEA, the solver said that we had geometric nonlinearity because we had large displacements. We've idealized the loading conditioning and the boundary conditions. These are very important things. We could go into this in a lot of detail about how we apply the loads and how we apply the constraints. And often that could be pretty important for a particular problem that we're working on. The loads are static, so we don't have that's as if we've slowly applied the loads so that we're not thinking about the dynamic loads if we put them on suddenly with some type of impact. So we're quite often, there are solvers and methods to put dynamic loads on things, just notably. We're usually dealing with four two-dimensional problems. We're saying that plane stresses, plane strains remain in a plane. And that's closely related to the deflections being small. The same type of deal. So here you go. Just as an idea of stiffness formulation, I use the simplest case would be if we had for the axial case, if we have the stress and the strain. Stress is F over A, strain is del over L. And then we can use Hooke's law. Stress is equal to E epsilon. And we could replace those two known things, the stress and the strain, in Hooke's law and come up with the displacement is FL over AE for the axial case. And it's important to note that for stiffnesses, that's F over del in general. So now we can come up with a stiffness. If we were going to create a stiffness matrix for an axial problem, it would be AE over L. Other displacements we might want to consider in the same type of mindset. What we're discussing here really is the step-by-step idea that we're going to create a K matrix, right? Or that someone who has created an FEA code has made an element, and that element has a stiffness matrix or stiffness properties. When we combine them with a bunch of elements together, we're able to formulate a stiffness matrix. So one that we know really well for torsion is TL over JG, I usually say. that we could think of it as having a stiffness, like in this case right here, where we've placed the load over the displacement, just like we did with the other stiffness. Or we could go and look up for a beam, a case where we have force and displacement. Here we're calling displacement y. So FL cubed over 48 EI could be a simply supported beam. Notably that the displacement and the force are in the same location. This isn't how it's actually done, but this is the kind of the main idea behind it, where you want to create elements that have stiffnesses by way of your element formulation. And the people who design FEA codes spend a lot of time and effort with their formulation of elements. She also mentioned the shape of the element has a big deal to do with these stiffnesses. That's often called a shape function, and there are a lot of effort placed into shape functions. But that doesn't matter to us right now. Let's talk about like the simplest case. Call it a two-dimensional element because we have two nodes. We have I and J. And we're only dealing with whether it's moving left or right in either case for the I and the J element. So we could easily take the sum of the forces equal to 0 to be able to balance this out for the applied load FJE. Let's say this right there. And more importantly, we could create two equations, do the same mindset, and have now this really important F is equal to K, call it U. And if you were using matrices, this is a column, this is a column, this is a square matrix, as you see right there. Right? And you could do a little bit of like holding one still and finding the others to try to make the case, or to really think your way through if you needed to. Now, here is the FEA aspect, is that we could take a bunch of elements and put them together. So if we were going to put some elements together, here's just two elements that we're placing together. Element 1 and element 2, and we're placing them together. Here they are as individuals, and you could work your way through to appreciate. Here's what happens when you assemble them together. And what we've just done now is we've meshed a real thing into two elements. Generally speaking, we use a lot more elements, but we can't use an infinite amount. Therefore, we are dealing with finite elements is the idea. So we take the stiffness matrices from the elements and combine them together. Notably, if you want to dig in deep, these are almost always diagonal matrices. I asked the question, why should they be diagonal matrices? It's really sort of an energy thing, is a good explanation of why they're diagonal. But I won't go into that too much. This is more, and if you took an FEA class as undergraduate or graduate school class, most of the time what you end up doing is having a class on how to formulate yourself if you, for some reason, want to create your own FEA code. But it's also good to know what's going on underneath the hood. Now, I'd mentioned that we have a stiffness matrix that we want to invert. And inverting the stiffness matrix is a pain. It's computationally a pain. So there's a bunch of different types of ways to try to invert that matrix, or to make it more efficient to invert the matrix. Quite often, the most are numerical solvers. And the best idea that you could, the best association you can make when somebody says it's a numerical solver, the association you should make is a guess and a check, where they make a guess about what the answer is going to be, and then they check and throw the numbers back in and see does that work, and then they see what the error is, and they go and they make a better guess, and then they make a better guess, and then they make a better guess, and they do it over and over again until it converges to a solution. And so there's so many convergence types of aspects, that it could be a really good source of error in the big picture, because they're using multiple convergences to try just to narrow down and to simplify the problem to come up with an answer. So you can't trust FEA to be the answer. There's many different things, sources of error, but the act of the numerical solver is a big potential source of error. So here is a problem this is actually the problem out of Shigley in chapter 19 as an example. I have added some things to it, so pay attention to this, where we have a gap right here, and a force that's being applied right to the center of this piece that has these dimensions: 10 inches, 11 inches, 10 inches, 12 inches. It must be made of aluminum, because that I happen to know that's the aluminum Young's modulus. The force is 1,000 pounds. The gap is 0.002, and the cross-sectional area of each is as mentioned here. And we want to find the reaction at the walls. Okay. It's always good to look at the reactions in FEA. The deflection at B, right? So that right here. And then the average stress in each measure, right? So these are the three things we're going to look at. I don't expect these to be the correct answer, by the way. We can make the stiffnesses the AE over L for each. Each has a stiffness. We apply some boundary conditions. Well, let's make an assumption in this guy right here that this closes right here, right? That right there with the 0.002, which I meant to put inches right there. We'll make the assumption that the boundary conditions are closed, that closes, the gap closes, right? So that force of 1,000 pounds right here makes it so that gap closes. By the way, we're doing that so this is easier to solve, just you know. So here's the big picture kind of idea, just like we had previously shown, where we have two springs in series. We're treating each of these elements like a spring. We throw in the numbers that we have up here for the stiffness, and we also I might oh, by the way, I'm taking the 1E5 to the outside of this. Here's the external load. Here's the boundary condition right here. That's the boundary condition. And these have helped us make this an easier problem, just to be clear. We don't have to invert the matrix, is a nice idea. If you just take a look at row 2, all the way through right there, you have an equation with one unknown. So that we can solve it. So we don't have to invert the matrix like we said we had to. And we're able to solve for that. And we're able to, and notably, that is larger than the gap was up here, right? That 0.002, we find that we got 0.005 right in there, right? 0.005556. So yes, the gap closed. And note that if 0.3 were free, the gap would close. Oh no, I just said that. Okay. Now we can also find the reactions at right here. You can find the reactions here, and boom. You can find the reactions right here. So those, otherwise we would have, yeah, gotcha. Okay. And notably, we could check the force balance. And that's actually a really good thing to do when doing FEA on something, is to make sure that the force is balanced, because it is a numerical problem. So maybe it wouldn't. But you could see right here how the forces have to balance, right? You got the F is in. Here's your reactions happening both at the wall on the left and the wall on the right. They better equal to 0. And they do. So now we go for the stresses. Notably, stress is not a nodal quality; it's an element quality. So we can place them in here and find what the stresses are going to be. Not hard to do. And then we could also, the strains are also not a nodal quality. Strains are an element quality. So we can use them with this scenario here and find out what the stresses are going to be, which confirms what we had up here, right? So that we didn't have to do both things. We could do that. So you could also look at the example in the book, by the way, and make a comparison to what I'm showing here. Now I have made some elements, beam elements, I believe I used, to try to duplicate what we have there. I think I have up here is a displacement, up here is a force, and right here is a stress in PSI, so that I can make a comparison. So here is the displacement. Here is what I said my hand calculation would be. I might have meshed some additional things, but it's such a small element. It's such a crude thing. I think I used such a crude mesh that I didn't really expect them to match exactly. They're gonna get in the ballpark. Up above, well, these match, but this is a boundary condition. So for the displacement right here, so duh, it should match. Because I set that as a boundary condition. I made the thing be 0.002. That's one of the, you can almost think of that as being a load that I put on here. But now I got reactions over there, and they don't exactly match, but they get close. And here again, same dealio. And then for stress, in the ballpark, and also stress in the ballpark. So I mean, just coming back through what we have right here. I didn't mean to make this video this long, but I'm gonna keep going with it. This is the beginning of your FEA journey. So it's good to take a look at these simple hand problems to kind of understand what's going on underneath the hood. We don't have to get them perfect to be able to appreciate them. Now, I put this in here as these are different elements that come out to some of this is history. They have gone a long way in their element libraries of different types of elements for different functions. Some of the most common nowadays are solid elements. They weren't always all that easy. A really important category, and not really shown here, are plate elements. These are like surface elements, which are usually just two-dimensional. But plate elements are some of the most difficult to generate, and many FEA codes have spent a lot of effort on doing those correctly. This is from another book by Bob Norton, and he's just showing that, and maybe the thing I want to take away from here are these mid-side nodes that are sometimes hidden from you, sometimes they're exposed. They definitely have helped to make quality meshes. The easiest mesh to make for automated mesh generators are the triangular ones. And it used to be in the history of FEA, those were overly stiff, but they've made a better quality element in the last 20 plus years. And so automatic meshing has become the default way to do things. But there was a time where you really had to spend a lot of time, if you're an FEA user, trying to figure out a way to make quadrilaterals for your meshes, to make things out of Legos and bricks. There was a certain amount of finesse and artistry to it, but not there anymore. There's some more just same things I just mentioned about different element types, especially the shell elements, the plate elements. They often will have these nodes onto the sides of them. The biggest problem is joining plates together or joining plates with other elements and making sure that the sign conventions don't be of the nodes that are adjacent to each other in transitions aren't like counteracting, so they're having incompatible sign conventions is one of the biggest I would say uh, obstacles to those really important shell elements. But there's a bunch, also the curvature of the surfaces are also really important. So let's see. More complex stiffness. Okay, so here's an example from an ANSYS Beam 4. All right, so SolidWorks simulation doesn't have a whole lot of different elements to choose from, but all the other codes, there's a large element library to choose from, and one of them would be maybe a Beam 4 for a 3D elastic beam, and each node on each element has, in this case, 6 degrees of freedom. So you'd have this big matrix. It's just one element, and of course we're substituting a bunch of variables. You could just tell from this that you have a pretty substantial single element matrix. And now, if you can imagine, for a thing that has large, a lot of complexity, there's going to be a bunch of different beam elements. You wouldn't just use one beam element between two transitions. You use several beam elements. You can imagine how big the stiffness matrix gets very quickly for a combined degree of freedom problem that could be pretty difficult to solve. So we need to talk about the sources of error in FEA, because you're sitting there playing around with it. The modeling, due to simplifications, we almost always have to do some simplifications when we model something. If you try to run FEA on a solid model you've created for some other function, maybe it was because you were going to 3D print it or whatever, just to visualize it, you're almost always going to cause yourself a lot of problems, because you really should make an FEA model for FEA, right? You don't want to mix and match if you can help it. There are different codes nowadays that have some simplifying features, or features to simplify it so you can run the FEA on it, so you don't have to model every aspect of a thing into your FEA. You have to know a little bit about how FEA works, so you don't try to include everything in the kitchen sink into a model and expect it to run. But you have to be have good judgment in when you do that. So there's the wrong geometric description, wrong material. It's usually okay. You usually don't make it. The load is often, if you're looking at reality, you have to make some type of some assumption about what the forces and torques and external loads are going to be on a thing. It is not always clear what the case should be. You might have to run a number of cases and simplifying assumptions to be able to get a definition of the load. Boundary conditions, similar. I mention often the simplest case I know of a messed up thing is if you have bearings on the end of a shaft, right here, these bearings, right here, I'm exaggerating, noticeably that they have a slope to them. And so you can't just put boundary conditions onto this region and hold it tight and get the correct results, because it would treat it like it was a fixed, or let's say it would treat it like it was like this right here, like there's the original conditions right there. And okay, like that kind of thing right there, where it would make it rigid here at the boundaries because of the boundary conditions you chose. And that would not model what the correct thing would be in the real world. Wrong type of analysis, for instance, linear versus nonlinear. The way that you mesh the thing can often really influence what the results are going to be, especially if you end up with weird shaped elements. Almost every FEA requires you to do a little bit of a mesh analysis, where you see what happens when you make the mesh smaller and smaller. If it starts to converge, you can see that, if up to a point where, okay, I get a better idea, I get a better feel, that's probably what the answer is for the localized stresses. But it could diverge as well, as we will describe in another class. Of course, obviously the number of elements, but through the thickness is really important. If you have a very thin thing and you've made only a couple elements through there, it's not really going to capture the physics. You really almost going to need to make, a much tighter amount of elements passing through there, so that you will capture the true stiffness of the piece. And that's very true for things that are like plates. And that's why you want to have a plate element as one of your choices. It could do a better job of modeling the behavior of a very thin thing than taking a bunch of solid elements and trying to squeeze them into the thickness. And also the element types, you need to look up and understand them a little bit better, and not just to pick them randomly from this element. And then, as I've mentioned, almost all of the finite element codes now don't do like direct solving of things. They use numerical solutions where they're entering in a guess and then they're solving it, and they're comparing their guess with what they know should be true, and they're converging into a solution. So that's a big so integration error is kind of related to that. There's also different solver types. You'll see there's a lot of options, and the more complex, I should say, this isn't really important, true, the more complex the FEA code, the more choices you have, and the more bad choices you can make. So just be on the lookout as you're using an advanced FEA code like ANSYS or Abacus, and you don't know how to what all of the different things are, all the different choices and solvers. You could pick the wrong thing. It's not meant for that, and you're misusing it. there's definitely a learning curve. We're going back there. There's a little demonstration of some FEA. Here's that problem from the previous class, 287 and 0.0831. Let's see what we have here. I believe we already looked there. We had 0.28, so that wasn't terrible. And then 0.0831 compared to 0.0832, not so bad, not too bad. So the big idea here is FEA can provide an answer, but not the answer. Just be on the lookout, or maybe not be on the lookout. Just be aware that simply because the computer makes a pretty color picture doesn't mean that it has done all of the things that are necessary to solve a problem. That is not necessarily the answer. It's just an answer. It's a calculator that you hit a lot of buttons. Note that FEA solves for displacements. This is the topic here today is deflections, and that's a good reason for that, because that's what FEA is really doing. It can get the strains and thereby the stresses, and so we often probably use stress most often, and we associate. It's a tool to find stresses, but what it does better than finding stresses is it finds displacements. And when we're talking about convergence, it converges to displacements much faster than it converges to stresses. And there's a lot of sources of error. Most of them are in the chair in front of the computer, right? You are the source of error. So don't think that what the computer says is gospel. There's some things we'll talk about in future classes I've crossed out here. But here you go. This is garbage in equals garbage out. That is our big thought. Yeah, if you throw garbage into your FEA, you're going to get garbage out of your FEA. So I'm sorry if this was too long of a video, but I decided I should make one. 47 minutes, and the class is 75 minutes long, so I must have said some other things along the way. There's some demonstrations I could also do a SolidWorks simulation to make this a little bit more meaningful. Well, I'll talk to you in class soon.